Record in progress.
Hey, everybody. Let's start lecture on 2.2. We'll call this 2.2a. This entire chapter is on limit of a function. So I'm going to start off with a couple examples. If we have f of x equals x squared minus 1 over x plus 1, and we'll take a look at how I'm going to get this in a little bit. Well, next chapter. We have something going on like this. If this is x and this is y, then here at -1, there is a hole in the graph. There's a hole. In fact, I want to make that a big hole so that you can see it easily. I could do something where I have something like, we'll say g of x equals absolute value of x plus 1 over absolute value of x plus, not absolute value of x plus 1, but absolute on top, not absolute on bottom. And if I draw the graph here, this is -1, this is +1. I'll make that note over here. This is -1 as well. At x equals -1, we have, it's called a discontinuity. All of these holes are called discontinuities. The plural form is discontinuities, like this. And we'll talk about more about discontinuities. I want to say it's 2.4, 2.5. But this is this graph right here. Maybe I'll make the graph match the color of the text. Call that, I'll overwrite this with green real quick. Or I could have one something like this. H of x is 1 over x plus 1 squared, like that. And when I draw this, again at -1, I have something like this. There is a vertical asymptote right here. We'll talk about that more in a little bit. But it's doing some stuff like this. Okay. So it's worth pointing out, for none of these three graphs, does x equal 1 exist. There's a hole there. There's no value there. But like saying DNE is an abbreviation for does not exist. This is standard. You'll see this a lot. Does not exist. But to say these don't exist really doesn't say very much. Like f of x, our green graph right here, it just has a hole in a line. But over here, like this can the line jumps. That looks weird. There we go. And on this one here, like it's going to infinity near it. So saying DNE, this isn't very descriptive. And please pause these videos if you need to write down more. That graph is not lined up right. This first one. I'm going to erase this green line real quick. I'm going to move it down some. I wrote the wrong damn thing. This would be -2. There, it puts the hole there. And it should cross at -1 right there. That's the actual graph right there. Okay. So the way we can tell is we could do some tables as we get near it. And as we did yesterday, or as we did in the getting ready section, for like f of x equals x squared minus 1 over x minus 1, we can do a little table of values, x, f of x, and we can't do -1. -1 doesn't work. But I could do values like -1.5, -1.1, -0.9, -0.5. That should be a plus right there. And when you do the calculator work, as we did in the do calculator work here, these values are getting closer to -2. As we approach from both the negative side and the positive side. That's like coming in graphically, coming in this direction, and the values are getting closer to -2 that way, and they're getting closer to -2 that way. Okay? And we'll look at more stuff graphically in a little bit. So when something like this happens, and like even though it doesn't exist there, what we say is we say the limit, this is called the limit of a function. And we use LIM to describe it. The limit of a function as x approaches some value a. We say the limit as x approaches a of f of x. Well, let's do the example we have. No, yeah, I already started this. The limit as x approaches a of f of x equals L, which is the value it is getting close to. And L is the limit. So we could say the limit as x approaches -1. That's what this reads as. X approaches -1 of our function x squared minus 1 over x plus 1. We say the limit is -2 because that's what the values are getting close to. Okay. So this limit thing, f of x has to exist in an open interval or region around x equals a. but not necessarily at A. I'm going to redraw that graph here of f of x equals x squared minus 1 over x plus 1 to illustrate some more ideas a little bit. We'll do more on graphics in a little bit, but I think graphically really helps like show what's going on here a little bit better. And we have the hole here right at this value. It crosses at the y-axis at -1, and it's doing that. So we can do something called one-sided limits. One-sided limits approach from just one side. If we approach from the left, we will write limit as x approaches a, and we put a little negative sign to indicate we're approaching from the left. If we're approaching that value from the right side of the graph, we say that the limit as x approaches a from the positive side like that. And it's elevated up, so it looks like an exponent. If you work out the table and the graph, look at the graph here, a limit is really like what y value are we approaching? I didn't give myself a lot of room right there. Let me redo that down below. I'm gonna rope-a-dope this and move it down. A limit is the y value that the graph approaches Apparently need to move it down more. As x approaches a. So that's why we were getting a -2. This value, this y value right here is -2. So like this is x equals -2, and we have y equals -3 there. And as we get closer, this value is getting closer to -2, and maybe -1.5. -2, this is like -3. At -1.5, we're at like -2.5. And we're getting, as we get closer, we're getting closer to that value. Same thing from the other side. At 0, this is 0, -1. But if I do -1 point or -0.5, I'm at about -0 point or -1.5. And we'll go, if you do the table, you'll see this is the case. I don't want to waste your time doing a big giant table like we did on the getting ready and that you're going to do today, because the table things aren't that exciting, but they are how we're going to approach it. And you don't need to watch a bunch of videos on how to do this when we're doing it live. Okay. So let's take a look at this one. When we do limit as x approaches a, or in this case, limit as x approaches -1 from the left this was x squared minus 1 over x plus 1. This is getting close to -2. And the limit as x approach -1 from the right of x squared minus 1 over x plus 1 was also -2. When the one-sided limits equal each other, we say that the limit exists. Shake my hand off, it's getting a little numb. Writing a lot here. I'm going to be a little bit more specific here. If the limit as x approaches a from the negative side of f of x equals L, and the limit, that's not how we do this, like this, limit as x approaches a from the right of f of x equals L. If these are true, yeah, I wanted to write if in front of there. Then limit as x approaches a in general, not from left or right, equals L also. This reverses direction. This does go the other way. If limit as x approaches a of f of x equals L, then limit as x approaches a from the left of f of x equals L, and limit as x approaches a from the right equals of f of x equals L. So it's true either way. We have a way in math to condense this. This is like saying if A is true, let me clean this up, make it look a little bit cleaner. If A is true, then B. Let's use capital A and B here. And then if B is true, then A. That's kind of like what I did here. If I call this section B and I call these two together A, then I had the same up there. The way we put this together in mathematics is we use an if with a double F, IFF. We say if A, then B. That means both directions are true. The double F means both directions are true. Okay. There are two basic ones that are like very universal. The limit as x approaches a of x equals a. and limit as x approaches a of c equals c, where c is a constant value. This is like saying f of x equals x here. And notice in this case, like this is the line y equals x, which exists everywhere, which exists for all values of x. So the idea of a limit isn't just restricted to points where it doesn't exist. We can use it on values where it does exist. The constant value one is doing like y equals -2. So f of x equals -2. And even if we did this at x, let's say it's around 0. It doesn't matter which value we do. If we do x equals 0, f of 0 equals -2. If I do x equals 0.1, f of 0.1 equals -2. If I do x equals -0.1, f of -0.1 equals -2. It doesn't even need to be anywhere near 0. I could do x equals negative or positive 100. F of 100 equals -2 because there is nowhere to plug in an x. Up there. I can't plug anything in. It's just -2 no matter what I plug in. This is graphically the line. It's my x-axis, is my y-axis, 1, -1, -2. That is this line right here. So it doesn't matter which value I'm going near, it's -2 no matter where. Okay. We'll take a look at g of x. I'm going to scroll back up for a second real quick and show you real quick. G of x was the one where we had it where it did this little hop right here, does a little jump. And h of x is where it was going to infinity. We'll do another video for that one. This one's getting kind of long.